that mean go?
I thought I closed my email. I just heard it chime. That's weird. Yeah, go. Go ahead.
So I remember I had jotted down that when converting to Z-score, you lose scientific validity. I don't remember if that was from the book, from the videos, or both.
Yeah.
But
Scientific precision, more so than validity, right? Um, I might have said in the video, who recalls this? Did I say scientific validity in the video? I think that is from the book.
Yeah.
I think a better description is scientific precision. Um, though I suppose, in the sense that it's also the validity because it's no longer a valid assessment of a relationship, right? The question though is what do I mean by that?
yeah, but I think you answered it. So in them not no longer being the true observation, is that then why?
Yeah, because you can't actually say like, okay, so I said in the video that a lot of the stuff that I look at, I don't have to worry about transforming to z-scores because it's frequencies of things, right? Like, so I look at number of drinks a person has consumed, and that's a discrete number, and everybody uses the same kind of outcome there, and so it would be problematic if I used a z-score to then predict number of drinks because it's like, well, one standard deviation in my predictor then equates to X number of drinks or X proportion of drinks, right? And this gets even more complicated because drinks are a frequency, right? It's not a continuous variable. There is a true zero, but there isn't like it makes no sense to center drinks or something like that, right? And also they tend to be heavily skewed with most people drinking 0, 1, or 2 drinks and then a few people drinking 30, right? But the point of all of this is that if you transform everything to z-scores, yes, you don't get an understanding of like if I were to consume 3 drinks, does that increase my risk of experiencing problems by like 0.7, or for every 1 drink I consume, I have an increased risk of experiencing 0.3 problems, assuming they were on the same scale, like 1 drink and 1 problem, right? But if it's on a z-score, then it's like, well, if my drinks increase by 1 standard deviation, which who knows what that is as a function of drinks, then I will experience a 0.3 standard deviation increase in problems. It's a tough thing to wrap your mind around. And it also varies an awful lot across, or it can vary an awful lot across samples, right? And so then that idea of a standard deviation difference can be really problematic. So, make sense? All right, let's talk about sets. So we have 2 different types of independent variable sets. Anybody remember what they were? Structural and functional sets, right? And what is a structural set?
IDs that are dependent on other IDs.
Okay, what do you mean by that? Who can give me an example of a structural?
You're talking about dummy-coded variables?
Okay, yeah. What do I mean by dummy-coded variables? We're going to have a whole class on this, on categorical variables. I'm going to give you guys a very kind of brief introduction here by way of variable sets, right? So let's do something. Dummy-coded variables, if we have a group, a bunch of people assigned to conditions, we normally think of doing this in an ANOVA, right? But it doesn't have to be done in an ANOVA. Regression handles it just as well. And regression does something else. It allows you to, control for things, which you can do with an ANCOVA, I get it. But it also allows you to look at interactions within each category, which you can't do in ANOVA. So let's do this. Let's go analyze regression, linear. Let's leave audit, oh no, let's get rid of the z-score audit prob. Let's get rid of all of our z-scores. And let's just go audit prob as our dependent variable. And let's put in drinker right here. oh, stop, before we hit go on anything, let's go data, select cases, and let's use all cases again. And just real quick, actually, you know what? I'm gonna flip over to Stata because I like Stata more. Tab, I can just do it faster. If we look at drinker right here, but let me zoom in a little bit. It doesn't let me zoom in. Anyway, drinker is broken up by 3 different types of drinker, or 4 different types of drinkers, technically. 0 means that they say that they don't drink at all. 1 means that they drink very, very little. 2 means that they drink at kind of a moderate level, and 3 means that they are kind of harmful drinkers or experiencing a number of problems. Okay. You'll notice that the largest group is 2. That's your typical college student. Almost 50% of our people fall into that group. This is all college student drinking data, by the way. Only 13% of a sample of 1,600 said that they didn't drink at all. So, also kind of typical of college students. But all right, so flipping back over to SPSS. Let's go analyze, regression, linear. And let's put in drinker as our predictor and audit problems as our dependent variable. We hit go. And we do see that drinker is positively associated with alcohol-related problems. There's a problem with this analysis, though, right? What is the problem with this analysis?
You don't know which drinker, which type of drinker?
I mean, yeah, we don't know which type of drinker. If we had drinkers coded as 0, 1, 2, and 3, and we put it in regression with drinker as a predictor, is that the same thing as doing an ANOVA? Why not? You're right.
Because here in ANOVA we get the means of the 4 categories, and we can visualize that what's the change in the mean when we go from those one category, but here it's not like that.
That is not what we get here, right? In fact, it assumes that drinker is some sort of continuous variable here, right? ANOVA does not assume drinker is a continuous variable. It assumes drinker is a categorical variable. Now we get an ANOVA table here. Let's do this. Let's go analyze, and instead of regression, let's do an ANOVA, univariate. Did you see where I went there? I'm sorry. Analyze, general linear model, univariate. Our dependent variable is audit problems, right? Our fixed factor, drinker. And we can hit OK. We're not going to grab any of the other stuff. Now, if those were the same, then we would expect our F for this to match our F for our regression model, right? And so the F for drinker here is 155.409. In our regression model, the F was 245.493. Very different, right? Not the same thing at all. So how can we do a regression model and get the exact same thing that we get with an ANOVA? We do that through categorical variable coding, right? And so here, let's do this. Let's go regression linear. Let's remove drinker. And we're going to put in drinker 1, drinker 2, and drinker 3. These are just, go ahead and put them in, and then we'll come back to what these actually are. But if I scroll over here, drinker 0 are people that are coded 0 who are anything, if they're coded 1, then they report that they are non-drinkers, okay? Drinkers 0 means these are the people that don't drink. Drinker 1, they're coded a 1 if they are in the 1 group. So you can see drinker right here. They're in the number 1 group. They're coded as 1. Everything else, whether it's 2, 3, or 0, is coded as 0 for drinker 1, right? For drinker 2, you're coded as 1 if what? If drinker 2 is coded as 2, yep. Drinker 3, you're coded as 1 if what? Drinker 3 is coded as 3, right? Yeah. So these are dummy coded variables that are only 0s and 1s. And the important thing is that everything else is always coded as a 0, which means that you are going to wind up setting any group that you want. You can only put 3 groups in this model at any given time. Otherwise, something is going to be set as 0s all the way across. And so what this does is when we run a regression model, it will say whatever group that we leave out. Remember in the video I said that we have G minus 1 groups for categorical coding. Whatever group that we leave out, the regression coefficients that we get from this are the difference between that reference group that's left out and this group. It's nice because in ANOVA, in order to get this information, what do we have to do? Post hoc tests, yes. So we ran our model. Let's flip back over here. Let's look at, we did an ANOVA up here for drinkers. We got an F for drinkers of 155.409, right? We have with our 3 and 1604 degrees of freedom. Let's scroll down here. Here's our regression model. Our F should be what? Should be the same. Oh, real quick. Yeah, it's there. I'm sorry. I went too fast. Oh, I didn't ask. Oh, so here is our R squared, 0.225, 0.224. This is in our ANOVA model, right? And our F for our regression model should be what? The same. Let's look at our regression model up here real quick. What was our F there? Or I mean, what was our R squared? Did I not get R squared? Oh, dang it. Oh wait, it should be up a little bit. Our R squared here was 0.133. In ANOVA, our R squared is 0.225 with an F of 1.55409. And in regression with 3 dummy coded variables, what is our reference group here going to be? The 0 group, which was what? No drinkers, okay. Here's our R squared, 0.225. What was our R squared for the ANOVA? I think it was the same, 0.225. Let's make sure. Yep, 0.225 in ANOVA, 0.225 in regression. And our F for a regression model, 155.409. That is the same F, right? We've got 3, 1604, total of 1607. Yeah?
Did you have to tell SPSS that drink 0 was going to be your reference variable?
No. How did SPSS know that drink 0 was my reference variable? It knows because I excluded it, right? We'll get there in just a second. I'm going to show you rather than just explain it. The way that dummy coding works, though, is you will have 3 sets of variables, and all of those variables will have 1 at some spot. And that means that that 1 is going to be in reference to a variable that is not in the model, but would be 0 all the way across. and it controls for the fact that there are ones in other spots that are not accounted for there, right? So it allows for the parsing out of all of these means based on the fact that there are a series of ones here, and a series of ones here, and a series of ones here, and all of those ones have to be different from a zero group that's not included. So we can actually test this. Yeah, go ahead. Shoot.
So our numbers don't match yours, but they're slightly different. I mean, it's a small difference, but I don't know why if we have the same data set, yours would come up.
This is a good question. Whose numbers don't match mine?
155.677.
155.677. Okay, did everybody do, everybody undid select cases, right? And what do you guys have for n here? Just scroll up to the ANOVA model. 209, 352, 761, 286.
I think we have the same in this when we ran the ANOVA, but then we go further.
In the
Yeah, you're right.
is everybody's different from mine?
Yeah, but we're all the same.
But it still worked. Like, oh, ANOVA and then there
No. We're not gonna play that game. Hold on a second. We did, what was it? Audit prob. And then 1, 2, 3. 155.68. Oh, I just lost everything. What the heck just happened there? I don't know. Okay, let's come back to this. You guys did not have one. What do you guys have? 155 point.
155.677. So
Oh, it's 0.68. Okay. Here's my guess. I am using a different SPSS than everybody else is, right? I'm using SPSS on UCF apps, and I'm guessing that it is not quite the same version, and there has been some sort of change. So,
There's 24.
what?
You're on 24, I'm on 25.
Yeah. So there's a.
24.
You're on 24.
I'm on 24. Wow.
Is it 24.000?
Well, on these computers, you can choose either 24 or 25.
I'm on 24 too.
Huh. That is weird. I am not sure what's going on. The fact that it doesn't match my.
I'm on 38 sometimes.
Hold on a second. Analyze, regression, linear, audit prob, drink 1, 2, 3. Did I do anything different in here? I don't know. That is puzzling. If you guys go here, are your slopes different as well? Oh, I hate this. I'm not sure why that's happening. I mean, but you guys are all getting the exact same thing that or the exact same thing as each other. That's super weird. I'm gonna hold on just one second. Data, select cases, all, okay.
Actually, also on that last thing you were looking at, if it's only drink 1, I think that has different numbers. All the rest of them are the same, and so it's probably something that's different between our drink weight. Something has to be there because the rest of the numbers are the same.
All right, analyze, regression, linear. I have drink 1, drink 2, drink 3. Audit prob, right? Okay. What do you guys have for a constant there? What is your constant listed in your regression equation? The important piece is that your ANOVA and your regression match, and my ANOVA and my regression match. It's frustrating that mine don't match yours, but
think Jacob is right. If you put the descriptives in, I'd say that drink 1 would be different. Because he's right, all of the numbers are the same except for drinker 1.
Except drink 1.
So, I don't know if
At
your
the very bottom,
descriptives
your
might be different.
coefficients, the coefficients match up for
Extra 0 or something in there. Might be 1.
Yeah, let me do this real quick. Analyze, descriptives, explore. Okay, so for that's not going to help. All right, we're not going to worry about it right now. We're going to just pretend like everything is the same. That is a little bit weird and frustrating, but such is life sometimes. Okay, so back to the question at hand. You guys have slightly different things for drink 1. You have the same thing for what does your constant say? 0.055. What is your drink 1? 0.047. What's your standard error for drink 1?
67.067.
What's your p-value then?
484.
Okay. Drink 2, what is your coefficient?
166.
And drink 3?
1.182.
That is weird. I don't know why that's happening, but we're also not going to spend too much time worrying about it. All right. So what can we glean from this table? This table actually tells us a ton of information.
Only drink 2 and drink 3 are significant predictors.
Say that again?
Only drink 2 and drink 3 are significant predictors of alcohol.
Okay, drink 2 and drink 3 are significant predictors of alcohol problems. Drink 1 is not. But is that really what we're saying here? So the thing with these types of sets, independent variable sets that are all interrelated, they only have meaning in the context of every other set in there, right? So it's not really that it's a predictor of alcohol problems. It's telling us something in relation to everything else in the model. And in this case, it's telling us something specifically in relation to non-drinkers. What is it telling us?
Less problems.
Non-drinkers have less problems. Let's start with that. What are the problems? How much problems do non-drinkers have?
Non-drinkers have 0 alcohol-related problems.
Well, almost 0, not quite. It's in this table. 0.055. That is our baseline, right? The 0 group becomes our baseline. That becomes our intercept. And this point is going to get hammered home when we start looking at interactions with categorical groups. But for right now, anytime you set a group as 0, then the intercept becomes the mean of that group. Let's do something quick. Let's go data, select cases. Select cases if drink 0 equals 1. Do I have to put equals in here? Is it just equals? It's just equals. Stata makes you go equals. Okay, we're going to select those cases. And then let's go analyze descriptives, explore. We're going to get rid of these, and we're going to put drink 0 in. And, oh no, we're not going to put drink 0 in. I'm sorry. We're going to put audit prob in. And this is going to give us our basic descriptive statistics for audit problems in the drink 0 group. Who wants to put a wager on the mean? 0.0547, which is pretty dang close to 0.055, right? Yeah. So if that is our mean in the 0 group, what does that tell us about these other groups? scrolling back up to our regression model.
So there is a significant difference between the drink 0 and drink 2 and drink 0 and drink 3, but there is no significant difference between drink 0 and drink 1
Right.
in terms of point probability.
Perfect. Even better. That's a great description. What is our mean in drink 1?
Oh, 0%.
Well, mine says 0.049, but nope, that's not the mean. Remember I said that everything in here is in relation to that 0 group? So what is our mean in drink 1? No, wrong direction though. Oh wait, 0.2, no. Drink 1, if we move from drink 0 to drink 1, we see an increase of 0.049, 0.047 for those of you at home. So what does that tell us about our mean for drink 1? 0.09, I mean, it's going to be like 0.102 or something like that, 0.103, depending on whose math you're using. Let's check it. Analyze. Oh, let's go data, select cases. Select cases if drink 1 equals 1. Okay. And now let's go analyze, descriptives, explore, same thing. And 1.039. You guys have something slightly different because you guys have 0.047 or whatever. I have 0.049. What do you guys have for a mean there? What's that? 0.037? Is that what you guys have? Or 0.103? What do you guys get for a mean for?
1018.
Oh, 18?
Or 1018.
Okay, 1018. Is that what everybody else got? And I'm guessing like if you add, okay, 0.05. Let's just pull out a calculator. 0.055 plus 0.047, is that right? Oh yeah, I get 0.102, so 0.1018 makes sense.
So
Yeah.
that's the arithmetic to get to.
Yeah, that's the arithmetic. So if we scroll back up then to our regression model, what is our mean in drink 2? I'm going to add it up here. 0.22, I think. 0.221, right? You guys have 166, don't you? 166 and 055? So it should be like 0.221, unless I'm adding wrong. All right. And so what does that actually tell you then about drink 2? They have what? If you were to describe the difference of that coefficient, how do you describe that coefficient?
Do we describe it in percentage?
I wouldn't use percentage. How would you describe that? It's a point estimate, right? You could say that relative to non-drinkers, moderate drinkers, we'll call them, experience 0.166 more problems or 0.221 problems on average, right? And the more important point here is that 0.166 more problems than the control group or than the non-drinkers is significantly higher, right? Significantly more problems than the control group. It's not actually telling you anything about the true number of or the true effect of being in that group. It's just saying relative to non-drinkers, it is this, right? I suppose if you add the slope of non-drinkers, you can say the average amount of problems amongst these people is this, and it's significantly more than the other group. And then finally, drink 3 are problematic drinkers. What is the mean of problematic drinkers? The mean number of problems. Yeah, 1.237. Yep, that is their mean. And how do you interpret that coefficient, though? What do you say?
So problematic drinkers have 1.19. The problematic drinkers have 1.23 more problems than non-drinkers.
No, it's not 1.23.
And 1.182.
Yeah, 1.182, right? You just interpret it just like that. Relative to non-drinkers, problem drinkers experience 1.182 more problems on average, right? Now, it doesn't tell you any type of linear trend or anything like that. It is a straight mean difference, right? But the take-home message here, what is, when we run this in ANOVA, and then we do post hoc comparisons, what do we have to do? Think about when you guys did ANOVA last year, you did your ANOVA, and then you did post hoc comparisons across groups, your mean groups. You have to do something, right?
We take the mean difference in the post-op.
Sure, yep, you take the mean difference, but you have to do a correction, right? You have to do an alpha level correction or a pairwise or family-wise correction. So does this sound familiar? So for every comparison that you do, you divide that p-value by whatever number, right? So if you're going to do 5 comparisons, you divide your p-value by 5, and now your significance level is 0.01 in order to say that there's a significant difference. The beauty of doing this in regression is it's all done in one simultaneous step. There's no need for any type of pairwise correction because you've got it, bam, right there, it's done, right? The other beauty, yeah, go ahead.
How can we interpret the difference between grade 2 and grade 3? Is it the same?
Yeah, so this is
Just the
this
same math?
this is a great point. How do you interpret the difference between group 2 and group 3? You can actually get all of that information from right here, right? But there's an easier way to do it. What's the easier way to do it?
We control for
So from right here, we know what the mean and standard deviation is for every single one of these, right? Or the mean and standard error of the coefficient. So we can technically calculate a t-test and a Cohen's d and everything for every group that's up there listed already. And we can find our t-value and go to a t-table and find our p-value. But you can do it simpler by doing this. Let's go analyze regression, linear, and we want to know what the difference is between group 2 and group 3, right? Let's just pluck out group 3. Now, we have to have 3 predictors in there because we have 4 groups. We have to have g minus 1. Can pluck in 0. This will give us everything relative to group 3, right? Just out of curiosity, who wants to make a prediction about what's going to happen with those coefficients? Are they going to change?
grade 0 will be significant for sure.
They should go negative.
2 might be insignificant.
Yeah, so directionally they should all change, right? Because everything was higher than the 0 group, everything's going to be lower than the 3 group. What's going to happen, we can predict precisely what will happen to the coefficient for the 0 group. What's it going to be?
Minus 1.182.
It's going to be exactly the opposite of what the 3 group was. The other ones we can't predict. We can work the math out, but we can't just simply flip the sign, right? Did I do something wrong here? Or didn't that work?
I got the same. I think you did. Did you select all cases?
Oh, yeah. Yes, thank you. Okay, so select cases, all. Thank you. And then let's go analyze, regression, linear. Our F did not change, despite the fact that mine's different from yours. This is the exact same model, right? There's nothing different about it. This 1.237 is just the slope from last time plus the 0.055 for the intercept, right? Drink 0 minus 1.182. If we jump up to the last one that we had, which is way up here, isn't it? Ah! Why did you do that? Okay, let's scroll up. 1.182, just the signs flipped, right? Now notice we have 0.049 and 1.666. Those are going to change drastically, because they're now in reference to drink 3, right? So Tore asked, what's the difference between, how do you figure out the difference between group 2 and group 3? You can calculate that difference from the last table. You can get the p-value and the t-value right here by just swapping these out. And you can do this for every one of them, right? Like if you want to know like what is the difference between group 3 and group 1 and group 2, then what would you do if you wanted to know the difference between group 1 and group 2? Just pluck out either one, group 1 or group 2, right? Make it that reference group, and you can do it that way. There is another way that we can do this, and it's through a different type of regression analysis, and it's called multinomial logit. Let's see. I don't even know. Remember when I said that there is when it comes to statistics, that a lot of people like to use these flow charts, and I hate those flow charts because there's a lot of different ways to get to the exact same result. Multinomial logit will get you to the exact same result. And let's see if we actually have non-parametric tests. Multinomial logistic. Let's go here. In this case, we actually will put drinker in as our dependent variable, and we'll set our reference category as the first category, which is 0, right? Audit prob. Ooh, yep, that looks right. I think that's right. I never do this in SPSS, so. Oh yeah, audit prob can't be listed like that, sorry. Analyze, where was that at in regression? Multinomial logistic. Here's where we need it, because it's continuous. And oh yeah, and in multinomial logistic, they'll actually give you some kind of intercept and then a slope that's relative to it, but you wind up getting like roughly the same stuff here. Is this right? Though it uses log likelihood ratio tests instead of F tests, just FYI. But it will give you the same kind of basic types of stuff. Let's flip back over here for a second. I'm wondering if what I did, I'm going to close this out for a second and then open it back up. Yeah, it's not, this actually is very different than the way that multinomial logit works in Stata. No, let's just not do that. No, the output that it's giving me is different. I'm sure that the basic statistics are not actually different. Shoot, wrong data set. Oh, Dropbox, ARM2, week 5. Let's do the new. There we go. Logit. Oh, it's still, I guess it is giving me the kind of roughly the same thing here, isn't it? It gives you an intercept in addition to slopes. Oh, and it's setting my base outcome as 2 here for some reason, but it doesn't matter. Let's rather than confuse things, let's just stick with our straight regression for right now. But you can actually calculate or do these models in like multiple different ways. Another way to do this would be, well, it doesn't matter. All right, back to our regression model here. Ugh, before I made a big mess of things. The point of all of this is that we are able to enter these things like this and look at pure group differences as a function of drinking status, right? And so this is an example of what kind of set again? Structural set, right? Like these things are all kind of interdependent. All right. The last thing that we're going to look at is a functional set. So let's do this real quick. Let's go analyze what is a functional set?
So from the video, you had said that there's sets that have unique and independent meaning.
They have unique and independent meaning, but for any number of reasons, they have some sort of rationale for holding them together, right? In this case, we have 3 different types of impulsivity: urgency, conscientiousness, and sensation seeking. And let's do this. Let's go plots. Let's get R squared, part and partials, collinearity diagnostics. And we don't need any of that. That works. All right. So let's look at audit problems. Let's put in urgency, conscientiousness, and sensation seeking. And let's just scroll down here to our basic regression table. We've entered all of these things in together simultaneously to predict alcohol-related problems, right? And what can we make out from this table right here? This is going to be our most important table. Is everybody with me? Did I jump ahead? So there's a few important things that we can glean from this table, right? First of all, we can find out the independent effects of our different types of impulsivity. And a question that we might have is, to what extent are these aspects of impulsivity tapping into something unique? How do we figure out if they're tapping into something unique versus not unique? Say that again? Yeah, yep, tolerance and VIF, right? And so for tolerance, what are we looking for?
Greater than
1.
Point one.
Yeah, yeah. Actually, yeah, greater than 0.1, right? As we get like below that, then we're problematic. For VIF, what are we looking for?
1 divided by tolerance is VIF, so it should be greater than 10.
Less than 10.
Less than 10.
Less than 10, right? And so here we see VIF all looks very reasonable. Tolerance, that looks really good. Like the closer to 1, the better, right, for tolerance. And so we can see in our model here that when it comes to predicting alcohol problems, we have 3 different types of impulsivity. They are not so related that they are redundant, and that 2 of them contribute in important ways to alcohol-related problems, right? Urgency increases the frequency of alcohol problems. Conscientiousness, or what we might think of as self-control, is associated with a decreased frequency of alcohol-related problems. And sensation-seeking does not predict alcohol problems. It will predict alcohol use, though, always does. Sensation-seeking is a weird kind of aspect of impulsivity. All right. You know what? Let's take a quick break, and then when we come back, we will talk about hierarchical regression, putting multiple sets in a kind of stepwise fashion. So, any questions before we take a break?
Will there ever be a case where the tolerance is okay, but the bit isn't, and vice versa, and you kind of have to make your own informed decisions?
So there will be times when one or the other is borderline,
Okay.
but they're related, right?
Yeah.
Tolerance is, or VIF is just tolerance divided by 1. So, yeah.
I have a question.
Yeah.
So like, we see the tolerance for sensation seeking is highest, but still it's not significant.
Yeah.
So basically the variance by sensation seeking is more, but it's not a significant variance.
Yeah. I mean, what is tolerance? What would you interpret that from? What would you interpret based on that kind of?
So tolerance is actually unique variance in the different variable because of this particular different variable.
It's actually not associated so much with the dependent variable, right? Tolerance has to do with the overlap in variance between the other independent variables and the dependent variable, right? And so tolerance tells you if something is just redundant because it's overlapping so much with the other independent variables in the model. Sensation seeking isn't, and in fact, if you look at a correlation between these 3 variables, you'll find that sensation seeking is the least correlated with the other 2. Consequently, you're going to have the highest tolerance, right? Make sense? Yeah, Rebecca.
And how did you get the directionality for urgency and consciousness?
So you see the slopes there, the B's?
Uh-huh.
Some of them have a negative sign.
Okay.
Yep. So, good to go? All right, cool. Let's take a short break. And when we come back, we will wrap up.